Welcome to Chemistry at Heineck High School. I'm Brian Brown, and today we'll look at our next set of notes dealing with solutions. Now, today we're going to look briefly at the very beginning here about factors that affect solubility. Remember, solubility is the maximum amount that can be dissolved of a solute in a given amount of solvent at a given temperature. But one of the major things that influences what you can dissolve is really what the types of substances are. So the type of solute is very important to how much can be dissolved in a solvent. And really this is related to something we looked at in first semester, which is the polarities of the substance. Polar substances, which are substances that have positive and negative regions, can be attracted to other polar substances. Opposites attract. But if you have a polar with a nonpolar substance, there isn't a strong attraction between the two. So your polar substances will tend to stick together, and therefore the nonpolar substances won't be dissolved or interact with them. So they tend to separate out. So the polar things stick to polar things. Nonpolar things have weak London forces, if you recall from first semester. So compared to another nonpolar thing, those things would interact with each other, but they're not going to be attracted to a polar. So really the type of solute, whether it's polar or polar with nonpolar, plays a huge impact on how much can actually dissolve. And the concept here is like dissolves like. So remember, like means similar polarities. So polar will dissolve in polar, nonpolar dissolve in polar. And you can see through the animation here that our polar substances are particles with partial charge within them, mixed together and attracted each other and ended up in one region, and our nonpolar substances, the things with uniform charge distribution and only weak London force of attraction between, tended to mix together. Now, the reason why the nonpolar things are on top is all about density. So the reason these things are interacting with each other on top and these things are interacting with each other on bottom really deals with the polarities of the situation. So the polar molecules are going to form stronger force of attraction with each other, and they're going to push out the nonpolar things. And the nonpolar things will evenly disperse with each other because of their weak London forces. So that's one major factor that affects solubility, is really the polarities of the substances that we're dealing with. Now remember, water is a polar substance. You can see a water molecule right here, and it shows the unequal charge distribution within the water. Now remember, it's partially negative and partially positive. Overall, it's neutral, like all molecular substances, but it does have partial negative and positive regions. It'll also be attracted to ionic things which have cations and ions. So one part of water would be attracted to the anion, one part would be attracted to the cation. That's something we looked at way back in the first part of notes. Now, second factor that affects solubility, remember literally how much we can dissolve, would be temperature. Now, one of the things you need to understand with temperature is this is a general rule. Solid solubility usually increases with an increase in temperature. And you can see in this graph that everything listed except for the sodium sulfate either increases slightly or dramatically with an increase in temperature. So as a general statement, it looks like, and these are all solid substances, it looks like solid solubility tends to increase with an increase in temperature. Now, if we saw a set of gases, it would look very different because water is a polar substance. Gases are non-polar substances. Therefore, they're not going to be very soluble. And as I heat up the water, since they're weakly holding on to those particles anyway, as the water molecules gain kinetic energy and moved around more, that would knock out those particles and they would leave the solution. And therefore, our solubility would drop even more. So gas solubility is the exact opposite of solid solubility. Gas solubility decreases with an increase in temperature. So the hotter you get pop, the less CO2 can stay dissolved in it. That's one of the reasons why we tend to drink cold pop, is to try and keep it carbonated for longer. Now, last situation that we'll look at that can affect the solubility of a substance is in water is pressure. Now, one of the things you need to understand is it has little effect on solids or liquids. So we're not going to be worrying about pressure changes and how it affects solids and liquids. What we're going to look at is when we have a dissolved gas. And this is known as Henry's law. Henry's law says gas solubility is directly proportional to the pressure above the liquid, which fundamentally means the higher the pressure of the gas above the liquid, the more we can force down in and cause to dissolve within the liquid. And as a direct proportionality, this is going to look like our other direct proportionality laws from last chapter, the gas laws, which we had Charles, V1 over T1 equals V2 over T2, and Gay-Lussac, P1 over T1 equals P2 over T2. Notice this law looks very, very similar to those because it's also a direct proportionality. So if I know the solubility of a substance at a given pressure, and I know what the new pressure is, I can calculate the new solubility. And that's one of the things you should be able to do for homework is apply Henry's law just like we did with other gas laws last chapter. So fundamentally, this only applies to gases. And remember, gases are not very soluble in water because it's a polar nonpolar situation. But we can actually carbonate pop and get a lot of CO2 dissolved in it, but only at a very high pressure above. And that's why unopened cans and bottles of pop feel so rigid and hard because they're under a very high pressure. And as soon as you open that 2-liter bottle, you can hear the pressure equalize as the pressure escapes the 2-liter bottle. And notice what happens instantaneously after you start to open and the pressure drops. You start to see bubbles of CO2 form and leave the pop. That's because under lower pressure, we can't dissolve as much CO2, and the pop is slowly going to lose its carbonation. And if we shook it, it would knock out that nonpolar substance even faster. If we got it hotter, it would be even less soluble and it would come out even faster. So we want to keep it pressurized and we want to keep it cold in order to keep pop carbonated. So think of Henry's law as a pop law. Under high pressure, you can dissolve more carbon dioxide, but as soon as you relieve the pressure, the carbon dioxide leaves. Now, if it leaves very, very, very rapidly, we call that effervescence. And we open that 2-liter bottle of pop, it starts to rapidly escape. Now, that actually creates an issue inside our can or 2-liter bottle. If above the liquid layer, we have a layer of bubbles that completely covers the surface of that liquid. So if we shake it up, we're going to knock out some of the CO2 and we're going to get a whole bunch of bubbles here above the liquid. Well, as we lower the pressure, that's going to cause more bubbles to form, and they can't just rise to the surface and burst. What they're going to do is they're going to push up, and they're going to cause this to come out the top. And the more bubbles we have, and the more agitated it was, and the less soluble that nonpolar thing is going to be, and the hotter it is, the faster it's going to effervesce, and that can create a huge mess. So effervescence is something most of us have seen. Every time you see a 2-liter bottle being opened, you're actually seeing effervescence at work. Now, the other thing I wanted to do today was introduce one of our more common types of everyday ways of looking at how much is dissolved in a substance. Concentrations can be very, very important in different situations. Something can be necessary for human survival at a low enough concentration, but too high in concentration, it can actually be quite toxic to us. So how much is dissolved in a given amount of water can be very, very important in everyday life. The different ways we have of measuring that are known as concentrations. So how do we measure how much is dissolved? We use a concentration. It's a measurement of the amount of solute in a given amount of solvent or solution. Now, with what we're going to cover in the textbook, we're going to always look at amount of solute in a given amount of solution. But there are different types of concentrations that are solute per solvent, like molality. But that's not something that you're required to know for first year chemistry, and it's not going to be on our semester final. So the concentrations we look at are always going to be solute per solution, and that's a useful thing to remember. Now, before we get into quantitatively measuring concentrations, brief mention about qualitative concentration. Remember the term concentrated and dilute. You've used it many times probably yourself in life. It's something I think most of you intuitively get, but you need to understand it at a particle level as well. Anything we would classify as concentrated means we have a lot of solute in a given amount of solvent or solution. When we call something dilute, that means there is less dissolved of that solute in a given amount of solvent or solution. So the more concentrated, the more is dissolved qualitatively, and the less concentrated, the less is dissolved. The more the dilute, however, the less is dissolved, and the less dilute, the more concentrated, and the more would be dissolved. So you should understand intuitively and be able to use appropriately concentrated versus dilute as a qualitative way, a non-number way of just talking in general about how much is dissolved. But we're going to be more interested in our quantitative way of measuring. So the first one we're going to look at is percent concentration. Now, percent concentration is useful in everyday products because most people understand percentages. We use them in everyday life. So when you say 20%, most people will get, oh, that means out of 100 particles in there, 20 of them are going to be that solution, 20 and 100. That's what percent represents. So most of the time when you buy something at a grocery store or a convenience store or a Home Depot type store, you're going to see the concentrations of the solutions you buy represented in percents because it's easier for people to understand. So it's usually used for practical household cleaners and pesticides and garden and medical applications. Now, there's two different types of percent by volume, and we use whichever is most convenient. So it can be percent by mass or percent by volume, but in both cases, it's the same thing. All percents are part over whole times 100. And we've already said the part is our solute, and the type of whole is always going to be the solution that we're looking at. So percent by mass would be the mass of the solute compared to the mass of solution times 100. I mentioned both grams here, but it really doesn't have to be in grams. They just have to be consistent. We could do it in pounds, we could do it in kilograms, we could do it in grams, and they'd all give us the same percent by mass if it's done appropriately. But we also have percent by volume. Sometimes we don't know the masses of the things. We're dealing with liquids and we know their volumes. So we can then calculate a percent as a volume ratio as well. Volume of solute over volume of solution times 100. So essentially the equations are identical to each other. The difference is whether we're dealing with masses as a ratio or we're dealing with volumes, but they're both a solute to solution comparison. Now, one of the things you have to be very, very, very careful of with percent by mass. So what we're looking at is this particular situation here. It is very common in a lot of problems to tell you the mass of the solute and the mass of the solvent in the problem. And that presents an additional step to our problem here. We can't just put one on top and the other on bottom because we need solute on top. Well, we're given that, that's fine. But on the bottom has to be the mass of solution. Well, how do we get the mass of solution? Remember, the solution is the solute plus the solvent. And one thing that is true of masses is they are additive. So watch out for percent mass where they give you the mass of the solute and the mass of the solvent. We have to add the two together to get our number on bottom. Don't just put the small one on top and the big one on bottom. That might be the case if they gave us the solute and the solution. If that's what they gave us, yes, we're just going to put this here and we're going to put that there. But if they give us the solute and solvent, we have to add them together. So always be careful of percent mass because there's two different ways these problems look. The nice thing about volumes is volumes aren't additive. If you have 25 milliliters of water and 25 milliliters of ethanol and you add them together, you don't get 50 milliliters. That's not how it works. So they can't give you the volume of the solute and the volume of the solvent because we just can't add them together to get the solution. So the nice thing about percent by volume is they're always going to give us the volume of the solute and the volume of the solution. Just be careful they're in a common unit. We can't take milliliters and divide by liters and get them to cancel. So here's a typical percent by mass problem. What is the percent mass of a solution containing 62 grams of sodium chloride dissolved in 1.2 kilograms of water? Now, first thing we have to recognize is what are they giving us? Are they giving us the solute and the solvent? Or are they giving us the solute and the solution? A really, really important difference because that's going to completely change the maths. Well, NaCl is my solute, so check. That's the same for both. But 1.2 kilograms of water. Well, water is the solvent that the salt is dissolving in. So that means they gave me the solute and the solvent. So to find solution mass, I'm going to have to take and add these two together to get the mass of the solution. So we got a couple things we need to worry about here. Remember our base equation, mass of the solute over mass of the solution, and typically we'll want both of them in grams. So one thing I see is, well, they give me the mass of the solute, so I can plug in 62 on top. But I've got two issues. One, this is not grams, and you have to remember, there is 1,000 grams in 1 kilogram. So you can do this pretty dimensional analysis if you want. So we've got 1 kilogram, and we want grams. That means divide by 1,000 here, and I'm going to end up getting 1200, which is where this number came from. That's one thing I have to rectify is I can't deal with grams and kilograms, so I need to get them both in a common unit. Easier to multiply by 1,000 than divide by 1,000, so I'm going to say 1,200 grams. Second thing, remember, solute plus solvent equals solution. So it's not 1,200 on the bottom, it's 1,200 plus 62. So it's going to be 62 divided by 1,262, And once you've got that, you're going to multiply by 100. Now, sig figs, a mention on that. Well, when we're doing the math here, we should end up with 2 sig figs because of our 62 grams. So we're going to round our final percentage to 2 sig figs, 4.9%. So that would be an example of a percent by mass problem. Percent by volume, it's going to look the exact same in general. And you do have to watch that you have a common unit. So let's change this problem a little bit. And let's say they said we had 62 milliliters of NaCl and 1,200 milliliters of water. Now, when I go to do this problem, I'm still going to have the volume of the solute on top, so that's still going to be 62. But on the bottom, I need, of a water solution. Really important change in words there. Well, now they're telling me the mass, or I should say the volume of the solute, NaCl, and they're telling me the volume of the whole solution, 1200. So I would not add the 1200 plus the 62. It would just be 62 divided by 1200 times 100. So remember percent by mass. You might have to add up what's the total and put it on the bottom, or they might give it to you. But percent by volume, they're always going to give you the volume of solution for putting on the bottom. And that ends our first type of concentration that you need to be able to calculate percents.